All right, welcome back, everyone, to the deep dive. We're constantly on the lookout for those fascinating cutting-edge stuff happening in the world of, well, everything, really. And today, we are going deep on something truly mind-blowing. I'm talking AI, I'm talking medical imaging, and I'm talking an absolutely colossal data set.
Yeah, this one's really something special.
So we're diving into the world of an AI system, a system that's been built from the ground up to analyze MRI scans of the spine, to spot problems, potential issues that might be lurking in there. And what's really captured my attention right off the bat is that this research, the paper you sent over, it's all based on a data set of truly epic proportions.
2 million MRI scans.
2 million. It's just, I can't even wrap my head around that number.
Yeah, that's the scale we're talking about here.
All right, so before we get lost in the technical weeds, which we will do eventually because I love that stuff, can you kind of set the stage for us, our mission, if you will, for this deep dive? What exactly are we trying to understand about this AI system and its potential impact?
Our mission today is to understand how AI is being used to, well, revolutionize the way we diagnose problems in the spine using MRI. We're going to explore the scale of this project, 2 million scans, what this AI is capable of doing, and ultimately what it means for the future of healthcare.
Exactly. And at the core of this whole thing is a seriously in-depth research paper that lays out the entire process, how they built this AI, how they trained it, even how they started using it in real-world settings. I got to say, when I first started reading through this, the thing that just jumped out at me was that number 2 million MRI scans. And they didn't just pull these randomly from the internet. These came from a huge network of hospitals and clinics across India.
Diverse sources, yeah. Real cross-section.
Absolutely. So let's unpack this a bit. Why go through the trouble of building an AI for this in the first place? What's the problem they're trying to solve?
Well, the research paper makes it pretty clear right from the start. Spinal problems, things like herniated discs, we're talking degenerative disc disease, spinal stenosis, these are super common, and MRI. MRI is the gold standard for looking at all that soft tissue, those discs and nerves, to diagnose these problems. The problem is it's a very human-intensive process right now. You have these highly trained radiologists. They have to look at every single scan meticulously and figure out what's going on. It takes time. It takes serious expertise.
So it's a bottleneck. We need more diagnoses, more people need these scans analyzed, but there's only so many hours in a day, only so many radiologists out there.
Exactly. And that's where this AI comes in. It's what's called a computer-aided detection system, a CAD system. And what's really exciting, what's really impressive is how advanced this particular system is. It's not just one AI, it's like a whole team of AI specialists.
Oh, okay. I like that analogy.
They each have their own skills. So you've got one set of models that's all about classification. They look at a scan and say, hey, this looks normal, or hold on, there might be something abnormal here. Then you've got another group of models that do segmentation.
Segmentation.
So once they've spotted something, they can draw an outline around it, like a digital map, pinpointing exactly where the issue is. And they use different types of deep learning models to do this, vision transformers, modified UNets. They even throw in something called MedSAM to make those boundaries super precise. And all of this entire system is trained on that massive data set of 2 million MRI scans, each one meticulously labeled by, you guessed it, expert radiologists.
Okay, so I'm starting to get the big picture here, but let's zoom in a bit. Walk us through the process. How does this AI actually take a raw MRI scan and go from here's a bunch of pixels to here's a potential problem?
Yeah, it's a pretty amazing journey. So first things first, data preprocessing.
Reprocessing. Sounds like getting all your ingredients ready before you start cooking.
Exactly. So you've got the MRI scans, but they come in a format called DCOM. It's standard, but not ideal for AI. So step one is converting those files into something called NIFT-TI, a format designed specifically for medical images. Then they do something called intensity normalization. Basically, they're making sure all the images have similar brightness and contrast, no matter which MRI machine they came from. This helps the AI compare apples to apples, so to speak. And crucially, they make sure they're looking at the right type of MRI images for spinal issues.
So they're filtering out the noise, focusing on the images that give the most information about the spine.
Right. Primarily those side view images, the sagittal T2 weighted images.
Okay, pre-processing done. What's next?
Next, they bring in the vision transformers, the VTs. These are like the AI's pattern recognition experts. Their job is to look at those pre-processed images and make a first-pass judgment. Normal or abnormal. They're really good at picking up subtle clues, things that might not be immediately obvious to the human eye. And to make this initial screening even more accurate, they use a clever trick called ensembling.
It's ensembling? It's like getting a second opinion, or a third, or even a fourth. They train multiple VIT models, each one slightly different, and then they combine their predictions. So instead of relying on just one AI's opinion, they're getting a consensus from a whole team of AI experts.
That's smart. Like in the real world, if you have a complex medical issue, you often want to get opinions from multiple doctors.
Exactly. So the AI is essentially doing the same thing. It's getting a more robust, more reliable initial assessment.
Okay, so they've pre-processed the images, done their initial screening with the VTs. What happens to the scans that are flagged as potentially abnormal?
Those scans move on to the segmentation phase. This is where the AI gets really detailed. It's like an artist sketching out the anatomy, but with incredible precision. They use a modified UNet, a type of neural network that's really good at this kind of image mapping, but they've added something called cross-attention to make it even better.
Cross-attention, what does that do? Imagine the AI has these tiny spotlights that it can shine on the most important details as it's drawing. It helps it focus, makes those boundaries super sharp.
So it's highlighting the areas it needs to pay attention to.
Exactly. And they use something called dice loss and DCE loss to train these models. These are like scoring systems that tell the AI how well it's doing compared to the expert radiologist's markings.
It's like grading the AI's homework.
Exactly. And they put a bit more emphasis on getting the overall shape of the regions right, rather than being perfect down to the pixel level. Then they use another model called MedSAM to refine those boundaries even further, just to make sure everything is super accurate.
Okay, we've gone from identifying potentially abnormal scans to having detailed maps of the anatomy and any problems. But how does the AI actually put a name to the problem? Like, is it a herniated disc? Is it spinal stenosis?
That's where the detection phase comes in. This is the final step, the diagnosis, if you will. They use something called a Cascade R-CNN, which is a real mouthful, but it's basically a very sophisticated object detection system. It has a component called a region proposal network, or RPN, which throws out a bunch of boxes, like little guesses about where the problem might be.
It's like casting a wide net and then narrowing it down.
Exactly. They use different size boxes, different shapes to make sure they catch everything. Then they use a powerful image analysis network called ResNet 101, combined with a feature pyramid network, which lets the AI look at the image at different zoom levels. It's like having a magnifying glass built in. And to link all this back to the original image, they use something called row-eye align. This ensures that the AI is focusing on the right details, the right pixels, for making the final diagnosis.
So it's aligning the AI's attention with the actual location of the potential problem.
Precisely. And this whole process, it goes through 3 stages, each stage refining the detection, making it more and more precise. Finally, they feed all that information into a set of layers that decide, okay, based on everything we've seen, this is most likely a herniated disc or spinal stenosis or whatever it might be. And they can actually classify into 43 different categories of spinal problems.
43. That's incredibly specific. So we've talked a lot about the AI itself, how it works, all the different stages involved, but let's go back to that massive data set for a second. 2 million MRI scans. That's just mind-boggling. Can you give us a sense of the diversity of this data?
Yeah, the paper goes into great detail about this. It's not just 2 million random scans. They made sure to include a really wide range of patients and scanner types. They have data from different age groups, from kids to seniors, with specific numbers for each age range.
So it's not just trained on, say, middle-aged adults. It can handle the unique characteristics of scans from younger and older patients as well.
Right. They also included scans from different MRI manufacturers, GE, Siemens, Philips, all the big names.
So it doesn't matter if a hospital uses a different type of MRI machine, the AI can still analyze the images effectively.
Exactly. And they also included a balance of male and female patients. The point is, they went to great lengths to make this data set as diverse and representative as possible.
Because in the real world, you're going to have all sorts of different patients, different ages, different health histories, different scanners, and you want the AI to be able to handle all of that.
Absolutely. But of course, with a data set this large, drawn from so many different sources, there are going to be variations in the quality of the images.
Right. Some scans are going to be sharper, some are going to have more noise, maybe the patient moved during the scan, all sorts of things.
Exactly. And the paper acknowledges this. They talk about variations in field strength, the power of the magnet in the MRI machine, which can affect image clarity. They talk about movement artifacts, technical inconsistencies between different facilities, even issues that come up when images are transferred electronically for remote review. They've seen it all.
So how do they deal with these data quality challenges? I mean, you don't want to train an AI on a bunch of blurry or distorted images.
Well, they used several strategies. First, those pre-processing steps we talked about, things like artifact correction and noise reduction, those help a lot. They also had systems in place to flag scans that were of particularly poor quality.
So they could either exclude those scans or at least give them less weight during the training process?
Right. They were very careful about data quality control.
Okay, so they've gathered this massive, diverse data set. They pre-processed it, they've cleaned it up. Now they need to teach the AI what to look for. And you mentioned that expert radiologists were involved in annotating the scans. Talk about that process. How do they make sure that those millions of labels were accurate?
This is where the human element comes in, and it's a critical part of the whole system. So they had these expert radiologists, and their job was to go through each and every scan, slice by slice.
That sounds like a very tedious job.
Oh, yeah, incredibly detailed work. They had to label any abnormalities they saw, and they also had to mark areas that were normal. They did multi-label annotations, recognizing that sometimes a patient might have multiple problems showing up on the same scan.
So they weren't just saying, this scan has a herniated disc. They were saying this scan has a herniated disc at this level and also some spinal stenosis at this other level.
Exactly. And they didn't just label the problems, they also did really detailed segmentation, outlining the different anatomical structures, the vertebral bodies, the discs, the spinal canal. They were basically creating a detailed map of the spine for each scan.
So the AI is learning not just what a herniated disc looks like, but also where it's located within the complex anatomy of the spine.
Precisely. And to ensure accuracy, they had 2 different radiologists review each scan independently. If there were any disagreements, they had a consensus meeting to figure out the correct label.
So it's like a double check system to minimize errors.
Exactly. And they also had to deal with variations in how the scans were acquired, different slice thicknesses, different coverage areas. They standardized the images as much as possible, but they also had to adjust the annotations accordingly just to keep everything consistent. It was a very rigorous process.
Wow. Okay. So They put all this effort into building this AI, training it on this massive, carefully curated data set. What were the results? How well does it actually perform?
The performance metrics are really impressive. For that initial normal-abnormal classification, they achieved accuracy rates of 98%, sometimes even higher. And for the more challenging task of detecting multiple pathologies, the accuracy was still incredibly high, up to 97.9%.
Those are some seriously impressive numbers.
What's even more impressive is that this level of accuracy was consistent across different patient subgroups. They broke it down by age, by gender, by the type of MRI scanner used, and the AI performed really well across the board.
That's really important because it means the AI isn't biased towards a particular type of patient or a particular type of scan. It can be used in a wide variety of clinical settings.
Absolutely. And the paper goes into great detail about all the different performance metrics. They provide tables showing the accuracy, precision, recall, sensitivity, and specificity for each subgroup. They even break down the performance for each of the 43 pathologies they can detect. It's really comprehensive.
And did the AI maintain this level of performance when it was actually deployed in real-world settings? Because that's the ultimate test.
Yeah, that's the real acid test. And the answer is yes, it did. They deployed this system across 13 different healthcare organizations in India, a mix of diagnostic centers, hospitals, and government facilities. And during the deployment phase, they analyzed over 100,000 real patient scans. And the results were very consistent with what they saw in the research setting.
That's really encouraging. It means the AI can actually handle the complexities and variations of real-world clinical practice.
And it's already having a real impact. They're seeing faster reporting times, increased diagnostic efficiency. The AI is helping radiologists identify those common conditions more quickly, which frees them up to focus on the more complex cases.
So it's not replacing radiologists, it's augmenting their abilities. It's giving them a powerful tool to help them do their jobs better and more efficiently.
Exactly. And the paper emphasizes that the radiologist is still in control. They review the AI's findings, they can confirm, modify, or even reject them. The human expert is still the final decision maker.
That's really important to emphasize. AI is a tool. It's not a replacement for human judgment, especially in medicine.
And the system is designed to learn from those human interactions. If a radiologist modifies the AI's findings, that information is fed back into the system so it can improve its accuracy over time. It's a continuous learning loop.
So to wrap this up, we've got this incredibly advanced AI system trained on a massive, diverse data set that can accurately detect a wide range of spinal problems. And it's already being used in real-world settings, improving efficiency and helping radiologists do their jobs better.
Absolutely. It's a really exciting example of how AI can be applied to complex medical imaging tasks.
It's a great illustration of the power of AI when it's done right. You need a massive high-quality data set, you need expert input, you need careful validation, and you need to keep the human in the loop.
It also makes you think about the potential for this kind of technology in other areas of medicine. If it can work this well for spinal MRI, what about other types of scans? What about CT scans, X-rays, ultrasound? The possibilities are really exciting.
Absolutely. And I think that's a great place to leave it. Food for thought for our listeners. Thanks for joining us for this deep dive into the world of AI and medical imaging. It's been a fascinating journey.